This is a plot of time here, and this is a plot of pressure here, and this is surface pressure at the Viking Lander 2 site, and this is pressure at the Viking Lander 1 site. Experiments that were worked out here around pretty much here in the 1970s, and so the Viking Landers had a pressure sensor on them every day. They made a measurement of the pressure of the atmosphere. And so you can see how it's varying wildly here. And these two are offset because they're at different elevations. So it's just like more high elevations on it at lower pressure. So this one is at a lower elevation. Higher pressure. And this, what you see right here, is I'm going to do a lot of comparison to models. Okay. And in atmospheric science, we use something called general circulation models. Where we put all the physics of how the atmosphere moves, all the thermodynamics and all the dynamics into it, and we calculate when it should be snowing and not snowing. And so here's a plot of what should be happening. Here's what's the best. So this is the first day of spring in the northern hemisphere. So let's just look at the northern hemisphere. So on the first day of spring in the northern hemisphere, this is the end of the winter. So you have the maximum snow on the surface. This is CO2 ice on the surface. So you have the maximum snow on the surface, and then the sun is shining on the surface, so the CO2 goes back in the atmosphere. And by the first day of summer, all the snow in the atmosphere, all the snow is gone back into the atmosphere, so you don't get any snow in the northern hemisphere in the summer. And then on the first day of fall, the sun is going down, so you start to accumulate CO2 snow on the surface again. And so you get this pattern, okay? And then in the southern hemisphere, the exact opposite of things happen. Two things for the total ice. You can see that even though we have a yearly pattern, that we actually have a semi-annual signal of what happens to the mass. So one of the things is, we're looking for parts of the building changing gravity field, and so really down at the noise level, so that we have some idea of what phase of your signal is and how to know where to start. Okay, so next slide. Okay. So we need to make some measurements to see if we can do this. And by the way, this was not part of the regular experiment with spacecraft. But can. So these are two spacecraft that are in orbit around Mars today, and what is actually used to make the measurements is just this antenna right here. This is the Mars Global Surveyor spacecraft, and this is the Mars Odyssey spacecraft. And both of these spacecraft are in Mars orbit taking data today. And so to make these measurements, we just use the tracking signal that's used to communicate with the spacecraft. So this slide. Okay. So it turns out that the way that you measure gravity from a spacecraft in orbit around the planet is just amazingly simple in principle, because it's just a Doppler shift. Okay, but it's really, really difficult to do in practice. Okay, so here's Earth. Okay, and here's let's just say we have a spacecraft that is in orbit around the planet. So it turns out the way you track a spacecraft is you send up a signal at a given frequency, and the spacecraft communicates back to Earth at a slightly different frequency, just so you don't get the signals moving and stuff. Okay, so you send this signal down, okay, and it has a known frequency, and we can measure this frequency incredibly precisely. Okay, and that's why we can do this. And but when the spacecraft appears to be coming towards you, so it's coming in this direction, the frequency of the signal gets blue shifted. And when the spacecraft appears to be moving away from you, the frequency of the signal gets red shifted. So it's just like an ambulance, okay? And of course, from the frequency shift, you can just get the velocity, okay? And then the derivative of velocity is acceleration. So this is not even rocket science here. And gravity is acceleration, so that's how you do it. You just use the Doppler shift. So this is first semester physics. Okay? But the deal is that we can measure these frequency changes so precisely that we can measure changes in the velocity of the spacecraft to 30 microns a second. Okay, so this is what no one thought we could do, but we can do it. And so that means that you can measure teensy-weensy changes in gravity around Mars if you could track the spacecraft well. Okay, that's fine. So what happens is we're always, well, not always, 10 hours a day, we're tracking the spacecraft, and that's all the antenna time we can get. So we track these spacecraft for 10 hours a day, and we've actually figured out, so many spacecraft around Mars these days, we figured out how to track 4 spacecraft at a time using the same antenna. So that's a good engineering story at some point if you're interested in that. So what we do is we take all this tracking data for a given spacecraft, and we calculate the orbit of the spacecraft, and I'll show you how well we can do that in a second. And we have to take into account all of these things. We have to, account for changes in general relativity. We have to account for the gravitational attractions of all the other planets in the solar system. Okay, because the magnitude of the signal that we're looking at here on Mars is about the same magnitude as Jupiter's gravitational effect on Mars, when it's coming around in its orbit just doing this mess. So you have to account for all these things. You have to take into account the fact that on Earth you have these antennas where you track the spacecraft on Earth, and the tectonic plates move and actually change the positions of the antennas by a few centimeters a year. Okay, so we take that into account, all right, and then we take into account the spacecraft is in the atmosphere, so you get a little bit. It's really tenuous atmosphere, but you get a little bit of drag on the spacecraft, and that's an acceleration, so you have to account for that. And then the pressure of solar photons, okay, also causes a very teensy-weensy acceleration on the spacecraft, and we have to account for that, okay? And so, but we do that, okay? Lots of radical students, okay? We generate this is just, and then it just becomes a big, sparse, least squares matrix, okay? And so we use just techniques of least squares, and we generate a set of normal equations, and then we just combine these normal equations, and we compute solutions. And we do this every 5 days. So we compute a new gravity field for Mars every 5 days, okay? And then we do covariance analysis, and we calculate weight parameters and things like that. But we're a little bit in production mode right now. But you can see that this is just linear algebra. Okay, so it's just that it's on, you get an observation every 10 seconds. So every 10 seconds since 1997, for multiple spacecraft. Okay, so next slide. Okay, so this is just a little bit of the kind of the key to doing this whole thing is the ability to know exactly where the spacecraft is in orbit around Mars with respect to the center of mass of Mars at any given time. Okay, because the amount that if you say we dump a whole ice cap, CO2 seasonal ice cap on Mars in the winter, okay, and we put that there, and we look at the spacecraft in orbit around the planet, the additional gravitational attraction of a meter of CO2 ice, okay, in the spacecraft flight, accelerates the spacecraft towards the center of mass of Mars by millimeters. Okay, and what this shows is that we can calculate. This is just some data for what the radial errors in our determination of the orbit of the spacecraft is. We can calculate this on a single orbit to 5 centimeters, okay, and that's not bad to know where something is in Mars orbit to 5 centimeters, okay. But we need to do better, and so all you do is just add together lots of orbits and you just beat down this. Okay, so it just goes as 1 over root again of the observations, with an observation every 10 seconds. So so you just can you can't beat down moisture every bit, and you go to the level where you can calculate these things. So again, another principle of mathematics. So, okay, so that just shows you next slide. Okay, but now what we want to do is we actually want to recover what the mass of each ice cap is every 5 days. Okay, and there's a number of different ways that you can do this. But I'm going to show you one way that we do it. And that is to say we need to have some a priori idea of what the shape of the ice cap is. Okay, so and it turns out we're not too sensitive to the details of what we assume a priori for the shape, but we need something to start with. Okay, and so to do that, we combine a couple of different observations. Okay, so here are some observations that tell us what the spatial extent of the seasonal ice cap is, and what this is actually pictures of is the brightness of the Martian surface at 1.06 microns. Don't ask why. Okay, but it's just the albedo of Mars. Okay, and so on the first day of spring, here we are at the end of summer, and this transition between green and blue here is the extent of the seasonal ice cap. So this, what we're basically trying to get out of this observation is the angular distance from here out to here. Okay, and then you get this brightening, here the processes we're not going to talk about. But here, all we're interested in is getting the size of the ice cap. And so this is the southern hemisphere at the equivalent season, so 180 Elsevex's winter. So here's both the first day of spring in the southern hemisphere. And so you can just see here, as time goes on, how the ice cap is going away. So what this tells us is the spatial extent of the ice cap. And then we need one other piece of information. We need to know the depth of the snow, the depth of the CO2 on the surface. That comes the next slide. Okay. Okay, so we can make just a model of this about what the cap size is in degrees for the northern and the southern hemisphere. So we make some function. Okay, all right, next slide. Okay, so then we need to get the depth of the snow on Mars. Okay, and so this is just a seasonal average, but we actually measured snow depth on Mars using an altimeter. Okay, and so we can measure heights on Mars, 10 centimeters. Okay, and so we can get an idea of what the height is as a function of latitude, and we can make then we can get the vertical part of the function. Okay, all right, next slide. Okay, so you come up with some model that is basically a cone where at the pole of Mars you get the snow is about 1 meter deep of CO2, and then at whatever latitude the brightness goes away, then you're at 0. Okay, so it's just some function that we can match to the altimetry. Okay, and then what we do is we just say, okay, well, we're going to populate this cone. It's basically a circular cone, all right, with a whole lot of little mass points that you can see here. So we put 25 per degree, and then we invert the data, just compute the mass, okay, and all those mass points, okay. And this is just to show you. We do this actually in spherical harmonics, which is the solution to Laplace's equation on a sphere, and so this is how we calculate it. And Laplace's equation just describes potentials. Okay, so this is just the gravitational potential. So again, this is just I guess we would take this in like senior math or something, where you do solutions to Laplace's equation. We do everything in spherical geometry. Okay, so then we just calculate that. Here we apply data. It's easier to put the data for the fit. Okay, so next slide. Okay, so then, but we have to invoke, to keep the problem from blowing up, we have to invoke conservation of mass like we have to do for any physical process. So we have to, at any given time, we can constrain the solution to say, and here when we recover this, we don't have any way of separating the atmosphere above the north polar cap from the polar cap. Okay, so we lump those together. So we say the north polar cap plus the atmosphere plus the south polar cap plus the atmosphere above that, and then all this rest of the part of the atmosphere has to equal the total amount of CO2 on Mars. We're assuming that's not changing. So we use that as a constraint. Okay, next slide. Okay. And then we have to somehow treat the atmosphere. It's difficult to calculate the mass of the atmosphere because the atmosphere mass just spreads out in a way we call hydrostatically. So wouldn't actually produce gravity anomalies very easily. Essentially, what we do here is we just take a model, and I'm not going to go into this is kind of complicated, but we take it, basically take the atmosphere, we smoosh it all down to point masses on the surface, okay, and then we just treat it as a mass sheet on the surface of Mars, counting through the different elevations from all of Mars. And this is an extremely complicated thing to do, but it comes to it. Okay, next slide. Okay, so then you come up with just some big function that describes everything. Now here's your function that describes the snow on the North Polar Cap, and here's your function that describes the snow on the South Polar Cap, all as a function of time. And then this is what the mass in the atmosphere kind of should be doing. Okay, and then we just do a big inversion for 75 days. Okay, so then the next few slides just show you what the day looks like. Okay, so here is a plot then of mass, okay, as a function of L sub s, and here L sub s goes from 0 to 360. Okay, so from here to here is 1 Mars year, 2 Mars years, 3 Mars years, and 1 Mars year is 687 days, 2 Earth years, because it takes Mars twice as long to go around the sun. Okay, now this blue curve is what a general circulation model will predict, knowing all the physics about CO2 exchange on Mars. This is what the GCM will predict should be happening with the mass of the North Pole. Okay, and then the red here, these are actually calculations of what the mass is every 5 days on Mars, all the things that I've just told you. And then the white is just a fit, running mean fit to the red observations. And so you can see they actually fit it pretty well. Okay, and then the next slide. Okay, that's, well, this is the same thing that happens in the South Pole. Actually, you see that the numbers are higher. The mass snows, you get more in the South Pole than the North Pole. And that just has to do with where the carry axis of the Martian orbit is with respect to the sun, and the fact that the southern hemisphere has a higher elevation than the northern hemisphere, so it snows more in the southern hemisphere of Mars than the northern hemisphere. Okay, and then the next slide then just shows you what the atmosphere is doing as a function of time. So the thing is, so we can see the seasons changing on Mars routinely. Okay? And so this is this is pretty exciting because we can then track CO2 movement on Mars. But the sort of where this work is going to is sort of really interesting. You go to the last slide of the presentation. Okay. There is some evidence that there is drastic climate change going on Mars today. Okay, that Mars is warming up. Okay, and so Mars actually undergoes ice ages in a way like the Earth does. And this is Milankovitch cycles due to the lateness of the planet, the tilt of the spin axis, and the eccentricity of the orbit. All these things sort of feed together in a quasi-chaotic. It's not chaotic. It's predictable that you get all these frequencies where you should get ice ages on Mars, where the planet's tilt changes, and actually right now Mars's spin axis tilts at about the same amount as Earth's does. It tilts about 25.5 degrees, okay, and Earth's is 26. But on Mars, the spin axis can tilt almost horizontally, in which case you get more sunlight at the poles than you do the equator, so the polar caps would move on Mars, okay, down to the equator. Well, if you look at, we have, since we have all these spacecraft on Mars, we take pictures of poles at different times. And here's a picture taken in 1999, well, 4 different pictures, okay? And look at 1999, and then look at the same places that were imaged in 2001. So here, this is, if you're looking at these things are pits or depressions in the ice cap, okay? And this stuff on top is the CO2 snow on a veneer of water ice that stays there permanently, because it never gets warm enough for the water ice to supplement away. And so what you can see here is, you get this thing coming out here, and here it's much smaller, okay? And then down here you get this protrusion coming out here, and there it's smaller. Okay, and so what you can see is here you get this depression coming out. Here it goes away. Okay, it appears that from one year to the next on Mars, you're losing not as much CO2 is coming out of the atmosphere. Okay, and so that it suggests that more CO2 in subsequent years is staying in the atmosphere. Okay, but the problem is that when you take images like this, this is 3 kilometers across this image right here. Okay, and so you take images, and because of data rate constraints, you only image about 10% of Mars at this resolution, and let alone to go back and image again. And so, as a consequence of that, you can't do, you can't take images of all the polar cap. And here you don't get a mass estimate out of this anyway. You just get some amount of it looks like there's less coming out in this year than there is in this year. But if you wanted to really determine if climate change is going on Mars, and you wanted to quantify it and say, how much you could, the rate we're going here, you're going to lose all the polar caps in 100,000 years, something like that would calculate. The only way to really measure it is quantitatively using mass estimations from gravity, and so I guess the message to take home from this is by just using simple simple principles of physics and fairly standard mathematical methods, partial differential equations analysis and linear algebra, that you can actually figure out if there's climate change going on another planet. So you don't have to use really super sophisticated mathematics. It's the kind of stuff that you guys learn in class, but you just have to apply it extremely carefully. And so you might be amazed someday, just like I'm amazed that you took all these classes and you figure out what am I doing with this. But then you think of something that you'd like to do, and you realize that you know how to do it. Okay? And I guess that's all I have to say. Yeah.
North Pole and South Pole. Yeah. I was wondering if there's this consistent error between the blue and the yellow and the white. I was wondering.
Like this bump right here?
Yeah.
I can talk about this. Okay. Yeah, very, very astute. I didn't want to go into a little detail, but it's kind of an important detail. And I think, well, I'm pretty sure that the reason for this is that we're going through, we have this problem, and I think there's, when you recover the north polar mass, you're also recovering the south polar mass, and there's leakage between the two. Okay, it's difficult. You don't have enough information to separate the signals completely uniquely. So it helps, if you have more than one spacecraft, if you have 2 spacecraft now, and then there's another spacecraft getting to Mars in March, where we're also going to do this, and I'm going to have an experiment on that. And so the more spacecraft that you have, or if you could think of another constraint that you could put on the solution, would be both conservation of mass to do that. But it's really just your ability to separate out a signal of the northern hemisphere from the southern hemisphere. That's a systematic error. That's a problem. But this we obviously kind of thought we could do it, so we tried it, but we couldn't even get funded to do this because no one would be able to do it. So that's another message. Somebody tells you you can't do something, you're wrong. So,
you were going through this whole list of things to take have special general relativity.
Both and special.
What's the clinics? How do you know when you're done?
You don't.
You do some backup check or something? Second way.
Well, they've been putting this code together since but you have to do a lot of analytical work on what the magnitudes of errors are. Like the other thing that we have to account for, which I never thought because this is a radio signal, you have to take into account the weather tracking stations, you know, and you have to take into account if there's solar storms, you know, and all of these things. And you can calculate what the magnitudes, you know what the magnitudes of all these errors are. So if we do error analyses constantly at what is the effect of all the things that we could think of, okay, and then you have to make sure that you're correcting for all the things that have an effect that's comparable to the size of your signal. So, you know, so there are some relativistic corrections that we don't make because their magnitude is smaller than what we expect the signal to be.
I mean, if you didn't take into account one of these things, would then you just be very clear from what you have is working?
Then you wouldn't know, well, then you would get the wrong answer, okay, because...
There's some way it's sort of obvious that you have to take something into account.
Well, it's not terribly, it's not terribly, it's, you know, it's a little bit of, I don't want to say black magic, but it is sort of, I mean, you know, it is, but it is, you know, it's that you have to look at these, you really have to do analytical work to estimate what the sizes of these are, and then you sort of, I mean, there are things that I'd like to measure on Mars that I can't measure because I can't get the noise down far enough, okay, and so how do you measure right? I mean, here the reason that we think we're on track is that we happen to be agreeing with the general circulation model pretty well, and we don't use anything about that circulation model as a constraint on the problem, you know, so we are not biasing the solution by saying we're starting with the right answer and then we see if we recover what we started with. So this is a completely independent check, okay, and so that's how we know that we're in the ballpark. Yeah.
Just on this same data, if you want to kind of do a little more,
Sure.
you can say there's only 4 frequencies that,
Yeah.
when you look at certain parts of it, that
Oh yeah. Well, this is fascinating, okay, because this is one of two things, okay. Either this is error, okay, or it's weather, okay. You know, on the Earth, the weather, you know, I mean, you get a storm coming through and the pressure really changes, you know, or you get a high pressure area and the you know, it goes up, and so this is, you know, this could be a storm.
that would be from excess mass from the
Yeah,
atmosphere.
it would be, so you have a snowstorm coming through on Mars. You know, now the seasons on Mars, the sort of variability, because Mars doesn't have present day oceans on the surface, you don't get as much, you know, exchange on a very short-term basis. You know, the changes are more smooth on a seasonal basis. But you do get dust storms that occur, regional dust storms, which change the heating in the atmosphere. And so, you know, so these, it is, we haven't gone through a look, but it is getting to the point where people are starting to believe that these things are real. I mean, people other than us, I don't know if I won't say whether they're real, but other people, you know, can now go and correlate and say, hey, did you know there was a dust storm here, you know, which would change, which would heat the atmosphere, you know, change the amount of mass coming out of the environment. And so that could be what these perturbations are. So I don't trust these observations well enough to know whether these excursions here are real or just errors. But you know, but the more data that we collect and you know, other people, I'm not going to do this, but other people can go in and compare what we're getting here to actual phenomena that they're viewing the surface with other sensors. You know, then we'll have some idea of what whether we're seeing real atmospheric excursions here. But isn't it wild? You can just, you know, predict the weather on another planet and take it through out the